In the last lesson, we used op-amps to make active low-pass and high-pass filters. Those two blocks are more than separate examples. They are building blocks. If we place them in the right order, we can keep only a middle band, reject a middle band, and control how smooth or sharp the transition looks. A middle band filter has two important edge frequencies. The lower edge starts the useful band and the upper edge ends it. Between them, the bandpass filter keeps the signal. Outside them, it attenuates. The band reject filter does the opposite. It keeps low and high frequencies but removes the middle region. The simplest active bandpass idea is a cascade. First, use a high-pass stage to remove low frequencies. Then use a low-pass stage to remove high frequencies. Because the stages are active and buffered, the second stage does not strongly disturb the first stage. The useful band is the overlap between them. For a bandpass response, we usually name the lower edge omega-1 and the upper edge omega-2. The bandwidth is omega-2 minus omega-1. The center frequency is the geometric mean. Omega-0 equals the square root of omega-1 times omega-2. Then Q equals center frequency divided by bandwidth. A band reject filter can be understood as two paths added together. One path is low pass, keeping the low frequency parts. The other path is high pass, keeping the high frequency parts. When the middle band is missing from both paths, the output has a notch or rejected band. The same edge frequency language still works for band reject filters. Omega-1 and omega-2 mark the two sides of the rejected band. The center frequency sits between them, and the bandwidth tells us how wide the notch is. In a real circuit, notch depth depends strongly on matching and component tolerance. Now add one design word, Butterworth. A Butterworth response is chosen for a maximally flat passband. That means no ripple in the passband and a smooth roll-off after the edge. It is not the sharpest possible transition, but it is clean, predictable, and very common. Filter order controls how fast the curve falls after the edge. A first-order section rolls off at about 20 decibels per decade. A second-order section gives about 40 decibels per decade. Higher-order filters are sharper, but they need more stages and more careful component choices. A practical workflow is this. Choose the shape, bandpass or band reject. Choose the two edge frequencies. Compute center frequency, bandwidth, and Q. Then choose the response family, such as Butterworth for flatness. Finally, split the design into active stages that your op-amp can actually support. Middle band active filters are sensitive to real-world limits. The op-amp needs enough gain bandwidth. The stages need suitable buffering. Capacitor tolerance can move the center frequency. Resistor matching can change Q or notch depth, so the final circuit should be checked with simulation and with the op-amp datasheet. Summary. Active low-pass and high-pass stages can be combined into bandpass and band reject behavior. The key parameters are the two edge frequencies, center frequency, bandwidth, and Q. Butterworth is the smooth, maximally flat option. Next, we can turn this intuition into higher-order active filter sections.